Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 47. We are discussing design of low speed contra-rotating fan. So in last lecture we started discussing about design of rotor 1. We have done our calculation at the mid station, we have done our calculation at the hub station, as well as we have done our calculation at the tip station. Then we were discussing how do we distribute our total pressure along the span at 3 different stations such that we will take care of what all constraints we have defined with, maybe in sense of say diffusion factor, de-Holler's factor, my camber angle, we will put on I for this kind of configurations. Then we have discussed about the comparison of say 2 different rotors, one that's what is having say total pressure ratio expected to be 1100 Pascal, and for presentation design this is what is say 1200 Pascal. And we realize when we are increasing our total pressure ratio expected from rotor 1, my blade twist that will be coming to be slightly on higher side. So here this is what we have discussed for say 1100 and 1200 Pascal pressure rise. You can see for 1200 Pascal near the tip region we are having this angle or say my camber that's what is coming to be slightly on higher side. Now today we will be discussing about the design for rotor 2. Okay. Now say when we are talking about the design for rotor 2, we are looking for say total pressure at the entry of rotor 2 and total temperature at the entry of rotor 2. So we can say my inlet pressure that's what will be equal to say P02, that's what is equal to P03. Okay. Same way we can say our temperature T03 at the mid station, that's what is equal to T02. So you can say my station 2 is nothing but that's what is representing exit of my rotor 1, and station 3 that's what is representing my entry of rotor 2. So here in this case if we are considering this as my pressure, we can say we are expecting our pressure rise of 800 Pascal at the mid station as per our design requirement. So I will be calculating with say my pressure ratio of rotor 2 at the mid station, and that's what is coming 1.008. Same way we can do our calculation for say delta T0, and this delta T0 for rotor 2 at mid station, that's what is coming say 0.79 Kelvin. Okay. What we are doing here, that's what is say we are started doing design for rotor 2, and as we have discussed we are making our assumption, that's what is say my absolute velocity coming out from rotor 1, that's what will be the entry velocity for the rotor 2, and that's the reason my alpha 2 at mid station that's what will be equal to alpha 3 mean. One more observation, what we are having is in sense of whirl component coming out from rotor 2, that will be the entry whirl component for say rotor 2, and you know that's what is having opposite sign. So this is what we need to take care of. Okay. Now if this is what is your case, we can say we can calculate what will be my beta 3, that is nothing but my flow angle with which my air that's what is entering inside the rotor 2. So it says my beta 3, that is my relative flow angle, it is coming 57.51 degree. Okay. Here in this case you can say this is what is say negative sign, that's the reason why it is getting added up. Now based on our comparison for say Euler's equation, we can calculate what will be my CW4, at the exit of my rotor 2. So if we are putting this, it says my velocity, that's what is coming, say minus 9.46 meter per second. We can calculate what will be our beta 4, that is, like the angle with which my flow that will be coming out, it is coming to be 44.42. Okay, and my alpha 4 is nothing but my absolute exit flow angle. If we are putting it is CW4 by CA, that's what is coming, say 11.94. Now sometimes when you are doing your design, it may be having say constraint, it says your exit need to be axial 1. So that's what will be putting my alpha 4, that's what is equal to 0. Maybe my CW4 also I will be taking that as a 0, and that's what will be putting whole lot of stress on design calculations. Okay, so we are not restricting ourselves with say axial outlet, and that's the reason you can see at mid station we are having our alpha 4, that's what is coming, say 11.94 degree. So based on that we can do our calculation for say my delta beta. Once this delta beta is known to us, we can move forward with the calculation of other velocity components. Again, since we are having our motors, they are having capacity of 15 kilowatt, that's what is a constraint, that's what was given to us. So we will be calculating what will be the power required for rotor 2. So here if you consider, again we are assuming our mechanical efficiency for rotor 2 also to be 75%, and our efficiency for the compressor we are assuming 85%, that's what is coming, say 7.43 kilowatt. Now once the flow angles they are known to us, we can do our calculation for the relative velocity components. So this relative velocity component we can calculate based on say u2 by sin beta 3, okay, and that's what is coming, say 82.7 meter per second. So we are having our relative velocity with which flow is entering. Okay, same way we can do our calculation for the V4, that is nothing but that's what is my exit relative velocity from the rotor 2, and that's what is coming, 62.05 meter per second. Okay, once this is what is known to us, we can do our calculation for de Haulers factor, that's nothing but it's a velocity ratio, relative velocity ratio, and that's what is coming, 0.75. Okay, now we can calculate our absolute flow angle based on my known alpha 4 angle, and that is coming 45.4 meter per second. So once we are calculating our relative velocity ratio, our next target that will be to calculate the diffusion factor, and for calculation of diffusion factor, as we have discussed earlier, we need to calculate what is our M factor, we need to calculate what will be our solidity. Okay, so this is what we are putting in sense of my M factor, and here you can say like M, that's what is coming, 0.29. Okay. Now for rotor 2, when we are doing our calculation for the pitch, so here in this case we are assuming our number of blades that to be say 17. Okay, because this is what is in line to what all design we are comparing with already existing rotors. Okay, and for that we are having number of blades for rotor 2, that's what is coming to be 17. No doubt when you are making your mainline calculation, once you are ready with your Excel sheet, you can play with these numbers, not an issue. Okay, so here if we are putting that, it says my pitch, that's what is coming, 0.05. We can do our calculation for the solidity based on chord, it says it is coming 0.9. Once this solidity, that's what is known to us, we can do our calculation for diffusion factor at the mid station for rotor 2, and that's what is coming, 0.43. Be careful in sense of putting the angles, beta 1, beta 2, here this will be beta 3 and beta 4. Okay. Now in order to calculate other flow angles, say maybe camber angle, deviation angle and the stagger angle, we need to have assumption of our incidence angle. So in line to what we have discussed for rotor 1, Here for rotor 2 also, our incidence angle at mid station we are assuming to be 0. Okay. If this is what is coming to be 0, we can say our camber angle, it is coming 19.18 degree. Same way my deviation angle, that's what is coming 5.96 degree, and my stagger angle, that's what is coming 47.92 degree. So by this calculation, we are able to have this axial seat at the mid station ready with us. So you can say this is what is our expected pressure rise from rotor 2, that's nothing but 800 Pascal. Okay. Now what all we have learned, say for our fundamental method, we are assuming our delta P0 at different stations, and since we have designed our rotor 1 with the tip loaded configuration, same train we will be using for rotor 2, that's what will be having, say, tip loaded configuration. And if this is what is your case, initially we can assume, say, my expected pressure rise near the hub to be 300 Pascal and near the tip region is say 1300 Pascal. Okay. Now if this is what is your case, what we can do is we will start doing calculation at the hub station. Same way we will be doing our calculation at the tip station. But we need to be very careful, we should not commit mistake like this design approach for rotor 2 for control rotating configuration, that's what is different. Okay, and your small mistake in calculation, that's what will lead to give the numbers that may not be acceptable. So be careful about that part. So if we are considering that as a case, we can say at the hub we can calculate our peripheral speed. Okay, now near the hub I need to have my pressure as well as temperature, because we are looking for calculation of pressure ratio as well as what will be my delta T0. So be careful here, near the hub region, whatever is my total pressure at the outlet near the hub, that's what will be the entry pressure for my rotor 2. Same way, what is my total temperature at the outlet of the hub for rotor 1, that will be my entry temperature for rotor 2. Okay. So these are the numbers what we are putting in sense. Now once this is what is known to us, we can do our calculation for the pressure ratio, and the pressure ratio near the hub, that's what is coming 1.003. Okay. Same way my delta T0 at the hub, you can say that's what is coming 0.3 Kelvin. Okay. Remember what pressure rise we are expecting, that's what is lower. We are designing for tip loaded rotor, and that's the reason why my delta T0, that's what will be coming lower in the numbers. So now based on this, we can start doing calculation for our beta 3, and as we have seen, my CW2 at the hub, that's what is equal to my CW3 at the hub, and that's what we are putting here. That's what says my beta 3 at mid station is coming 46.56 degree. Okay. And now once this is what is known to us, we can do our calculation for the whirl component. Okay. Here in this case, we need to be very careful. Say here my work done factor, that's what I have taken as 0.88. For my rotor 1, we have considered that as a 0.98, and here this is what is say 0.88. This is what is based on what all we have discussed in our earlier class. Okay, and that's what is giving me my CW4 as minus 9.98 meter per second. So minus in sense, you need to be very careful about what will be my angle and what will be the direction. Accordingly, you need to do modification in your triangles. Okay. Now, if this is what is known to us, we can calculate what will be my alpha 4. Okay, my alpha 4, that's what is coming 12.67 near the hub region. If you recall, at the mid station also, that's what was coming around 11 degree, and we can do our calculation for beta 4. Now for rotor, when we are saying, we are always interested in delta beta. So at delta beta at the hub for rotor 2, it is coming 15.31. Okay, and my specific energy based on our understanding, that's what is say Cp delta T0. If we are putting, this is what is a number, that's what is coming. Okay, it is 0.29 kilojoule per kg. Now, once we have calculated our flow angles, we can calculate what will be our relative velocity, because we are interested in calculating our de Haulers factor near the hub region. So, if we are calculating that, say my V3 at the hub, it is coming 64.58, and my V4 at the hub, that's what is coming 51.94 meter per second. That's what is giving me my de Haulers factor to be 0.78. So, near hub we are having this de Haulers factor, that's what is coming 0.78. Okay. Now, based on that later part, as we are doing calculation, the sequence of calculation, that's what will be remain same when we are designing say rotor or rotor 2 in line to what we have done calculation for rotor 1. So, we will be calculating our pitch, and near the hub, as we have discussed, my pitch, that's what will be coming to be lower. Here for rotor 2 we have assumed our number of blades to be 17. So, that's what is giving me my solidity at the hub, it is say 1.8. Okay. Now, once we are calculated with the solidity, we know what will be our beta 3, what will be our beta 4. We can do our calculation for the diffusion factor near the hub region, and if you look at this number, that's what is coming 0.11. Okay. Now, for say calculation of our angles, we are looking for say our M factor, or say what we say Carter's factor, that's what is coming to be 0.32. Okay. Now, once this is what is known to us, again do not forget, when we are doing our calculation for say camber angle, say deviation angle and stagger angle, we need to have certain amount of incidence to be assumed, and as we have discussed near the hub region, we are assuming our incidence to be positive incidence, and that too we are taking positive 2 degree. So, if we are putting this, it says my camber angle at the hub, it is coming 17.42, my deviation angle is 4.11, and my stagger angle, that's what is coming 35.85 degree. Okay. You can cross verify this once you are doing your pen and paper calculation, that's what will give you the idea for the calculation. Okay. Now, similarly, we will be doing our calculation near the tip region. We will be having the same step, that's what we need to follow. We will be calculating our peripheral speed. Same way, near the tip region, we need to have our total pressure and temperature, that's what is coming from rotor 1, that will be the entry condition for my rotor 2. Now, once this pressure and temperature, that's what is known to us, we can do our calculation for say what will be my pressure ratio at the tip, and that's what is coming 1.013. My temperature rise delta T0 at the tip, that's what is coming 1.27 Kelvin. Okay. Now, based on all this calculation, now later part we will be calculating what will be our blade angles or relative flow angles. So, my beta 3 at the tip, that's what is coming 63.39. Okay. And when we are comparing our aerodynamic and thermodynamic work, that's what will be helping us for calculating what will be my CW4 at the tip region, and that's what is coming minus 9.26 meter per second. Okay. Now, once this relative velocity, that's what is known to us, relative flow angles known to us, my absolute components are known to us, later on we will be calculating the parameters called say de Haulers factor and my diffusion factor. So, let us move in that direction. So, it says I will be calculating what will be my alpha 4 at the tip region. We will be calculating what will be our delta beta, and if you look at near the tip region, my delta beta is coming 9.81. Okay. So, these numbers, that's what is having certain meanings. We will see when we will be discussing about, say, finalization of this design, what all is the meaning of these numbers. Now, as we have discussed, we are looking for our relative velocity ratio or say de Horler's factor. So, we will be calculating what will be my V3 at the tip, what will be my V4 at the tip, and that is what is coming 99.12 meter per second, and V4 is coming say 74.77. Okay. If you keep on eye with these numbers, you will realize my V3 that is what is coming to be higher, my V4 that is what is coming to be lower, and that is what is giving me my relative velocity ratio as 0.75. Okay. Now, in order to do the calculation for the pitch, we will be having say my pitch is given by pi d into say z divided by z. We can say our number of blades what we have selected is say 17. So, that is what is giving me my pitch, that is what is coming 0.075. Okay. And my solidity, if we are putting our chord to be 0.045, solidity that is what is coming 0.6. We can do our calculation for a diffusion factor at say our tip region, and that is what if we are putting our numbers say beta 3, beta 4 and my solidity, it is coming 0.48 near the tip region. Okay. We will be calculating our M factor because we are looking for other parameters or flow angles to be calculated. So, if we are putting this here, when we are calculating our camber angle, say my incidence angle at the tip, that is what need to be assumed, and as we have discussed earlier for rotor 1, in line to that for rotor 2 also we are assuming our incidence angle to be negative 2 degree. Okay. And if we are putting this as a number, it says my camber angle it is coming 18.61, my deviation angle it is coming 6.8, and my stagger angle that is what is coming 56.08 degree. Okay. So, now at mid station we have done our calculation, at the hub station we have done our calculation, at tip station we have done our calculation. So, like let us see what all we have assumed and like how this is what is affecting. So, here if you look at this is what is say the initial case what we have planned for, say it is having say pressure rise of say near the hub region it is 600, at mid station we have capped 800, and at the tip that is what is been say 1200. If you are looking at it says my de Horler's factor that is what is varying from 0.66 to 0.77. Okay. Now, if you look at the diffusion factor that is what is say 0.49 at the hub and 0.46 near say my tip region. Okay. And if you are looking at my camber angle that is what is coming 35 and 18 degree. Now, if we look this carefully, when we are expecting our pressure rise from the rotor 2, we need to keep on eye for certain parameters, and here for this target we have keep on eye for say our diffusion factor as one of the parameter near the hub and tip region. So, that is what we have done here. So, you can see we have reduced our diffusion factor near the hub region and we have increased our diffusion factor near the tip region. Okay. And that is what has been done by changing my delta P0 at the hub, say that will be reduced to say 300 Pascal, and this is what has been increased to say 1300 Pascal. Okay. Now, if you look at my camber angle accordingly, that is what is coming 17 degree and 18 degree. Now, with this all if we are putting, this is what is giving me say my overall distribution. So, if you try to look at this is what will be the distribution of my total pressure. Again for rotor 2 also this is what is designer's choice. Say here I have taken 300, maybe you can go with 400, maybe you can go with say 500, nobody will stop. It is your choice. But when you are doing that calculation, you need to do this calculation carefully, and as we have discussed, we need to check with total pressure rise, average total pressure rise throughout my span that need to come as per my expectation. Okay. So, be careful about doing this calculation. Here in this case, if we look at, this is what is representing my systematic variation of delta beta. You can say we are having the variation of say diffusion factor, as we discussed. We are having this diffusion factor as one of the keep on eye kind of parameter. If we are looking at the camber angle, this is what is representing my variation of the camber angle, and de Holler's factor also, if you look at compared to earlier case, we are modified with. Okay. Now, we have discussed for say rotor 1, we have assumed our say deviation angle, and that is what again say for this rotor 2 also we can assume our deviation angle to be say assumed deviation angle of 4 degree. If that is what is your case, you will be having say corrected deviation angle. Based on that corrected deviation angle, we need to calculate corrected camber angle as well as corrected stagger angle. So, we will be having all this calculation for that. And for this case also, let us say if we look at, we have assumed this deviation angle to be 4 degree. Now, this is what is designer's choice. Again I am telling, like it is not that 4 degree, you can go with 3 degree, you can go with 5 degree. But that is what need to make the sense in sense of what performance you are expecting. Many times it happens maybe from say hub to tip, you need to have the variation of deviation angle, and maybe from say mid to tip region you will not be having variation of deviation angle. Sometimes it may happen that you need to keep on eye, your deviation angle will be varying all the way from say your hub to tip. I am talking about assumed deviation angle. So, this is what is a number, that is what is in your hand, you can play with based on what understanding or what flow physics you are expecting. And once we are putting this, this is what will be giving me in sense of corrected camber as well as corrected stagger angles. Okay. Once this is what is ready with, we will be doing or we will be checking with how my variation of the flow angle, that is what is coming. Now, you can understand here our expected pressure rise, it is say 800 Pascal. So, my delta beta variation, if you are looking at, that is what is coming to be on the lower side. So, just look at, this is what is representing my delta beta variation. Okay. And this is what is a variation of my delta beta. Okay. Now, same way if you are looking at say my diffusion factor for rotor 1, that is what is having say high load and low load kind of configuration near the hub, my diffusion factor, that is what was coming lower. On say tip side, I am having say my diffusion factor to be larger. Okay. But at the same time, you are having say great control of diffusion factor for rotor 2. So, basically how nicely you are doing your design for rotor 1, that is what will be getting reflect on rotor 2. Okay. So, when we are doing our design for contra rotating fan, you need to design your rotor 1 nicely. Just finalize all parameter using your Excel sheet program. Okay. Once you are confident with, then you go with say design of rotor 2, because they are interrelated. Your small change for rotor 1 that may bring more change in rotor 2. So, be careful about these aspects. Here if you look at my de Holler's factor for rotor 1, we are getting very high near the hub region. In compared to that, we are having our de Holler's factor, that is what is coming to be lower. Now, you must be knowing the reason. We are talking about the relative velocity ratio. Okay. Now, once you are doing all this calculation for 800 Pascal, what we are discussing, this is what is a configuration or the blade, that is what we are achieving for rotor 2. Just look at, this is what is my rotor 2, and we are having say hub, mid and tip section. We are having 3 sections. This is what is the twist of the blade what we are getting for 11 station. Now, this is what is the case when we are having 1100 and 900 Pascal expected pressure rise. Okay. If you compare these two, it seems to be a similar kind of thing, but here if you look at, you will realize the difference for say how my angles or how my blade geometry that will be look like for two different configurations. Okay, here in this case we are having combination of 1200 and 800. So for 1200 what we have realized, we are having our flow angles, that's what is coming to be larger near the tip region, because we are designing highly loaded rotor, that's what is near the tip region. Now when we are comparing for say 800 Pascal and 900 Pascal, we will be realizing say when we are having this to be say 900 Pascal, our twist, that's what is coming to be slightly on a larger side. Major change we are finding towards the tip region. Near the hub region, not much modification, that's what can be observed. So like this, you can play with the number of parameters. Now here in this case, what all we are discussing is say distribution of my total pressure ratio. The question may come, sir, I am planning to do design for contra-rotating configuration in which I will be having my rotor 1 that will be rotating at high speed compared to rotor 2. Yes, same way, same logic, same calculation you need to do. You make your same Excel sheet program and you can play with the parameters, you can play with the numbers and get what you are looking for. Someone will say, I am not interested in say increasing the speed of rotor 1, I am more interested in increasing the speed of rotor 2. Yes, that is also possible. And if you recall, when I was discussing about the performance map, what we have achieved experimentally, it says when you are increasing the rotational speed of rotor 2, that's what is improving the performance in sense of pressurizing capacity. At the same time, we will be having some compromise in overall operating range. So this is what is designer's choice, what all he will be looking for. Okay, and as I told in one of our latest publication where we are having study for say distribution of total pressure ratio between two rotors, and when we are loading our rotor 1 too high, you will be having more chances for your flow to get separated near the tip region, and that's what will be making the design more challenging. So maybe you need to go with slightly higher loading for rotor 1, not too much loading for rotor 1. And the advantage of having higher loading of rotor 1, we have realized that's what is giving me say stall free operation, and that's what is increasing my overall operating range. Now in next lecture we will be discussing about the design for the same configuration using free vortex concept. So be with me. Thank you for your kind attention.